She did. Also, now we are online, yeah. So she did her PhD defense in St. Petersburg together with Semenyov and Viktor Sergeyev. And yeah, since 2016, she's part of the institute, so in Lucas Group. And so the stage is yours. Thanks.
Thank you. Thank you for a nice introduction. As Daniel nicely told, I'm working in the group of Luca Fossati, and I study mainly the hydrodynamic atmospheres and the atmospheric mass laws. And today I'm going to speak about the atmospheric mass laws through time. Since we have people from very different scientific background here, I will start with quite a general introductory part describing which types of the atmospheric mass laws do exist and for which specific atmospheres and planets they are important. And then I will make little discussions on how does it change through the planetary evolution. So to start, what is essentially the atmospheric mass loss? Atmospheric mass loss or escape is any process which brings out the atmospheric material from the gravitational well of the planet. And this process can be driven by the very wide variety of different processes, which can be formally divided into the thermal processes, which in this or other way have to do with the atmospheric heating, and the non-thermal processes guided by other forces. Among the thermal processes, the most classic form is so-called Jeans escape, which considers the escape of collisionless atmospheres, assuming that only the fastest particles in the atmosphere can escape. This is applicable for atmosphere with a very moderate energy budget, and for those with a high energy budget, this escape switches to the hydrodynamic escape, which can be powered by different sources. Again, the most classic case is the atmospheric heating by stellar high energy irradiation that is guided mainly by the photoionization, but it can also be driven by the combination of the own high thermal energy of the planet and its low gravity. Further on, one has to account for the interaction of the planet at close-in orbit with its host star, which can be somewhat twofold. So the stellar gravity can directly impact the atmospheric material, intensifying, for example, the hydrodynamic escape. Or on the other hand, the tidal interaction of the planet with its host star can provide additional heating, and additional heating always means intensifying the thermal escape processes. Further on, for the evolved planetary system and terrestrial-like planets, the important part is interaction with stellar winds, which can remove the atmospheric particles through the processes like ion pickup, can lead to the erosion of planetary atmospheres if they are not protected in any way, or can provide some additional heating at the thermosphere by the interaction of the energetic particles of the stellar wind. Finally, for secondary atmospheres, the important atmospheric mass source is the various ion escape processes, which can occur also for non-magnetized and magnetized planets, such in this case relevant ones are the acceleration of the particles in the field or the ion outflow. So the important thing about all these processes, they're gonna occur essentially at any planet and for any atmospheric type all the time. But their relative relevance is different And for example, the more global scale processes here in the group in the middle, I expect it to be most relevant for the primordial hydrogen-dominated voluminous atmospheres, while the kinetic-like processes on the flanks are going to be most relevant for the compact secondary terrestrial-like atmospheres. Here, when I say terrestrial-like, it does not necessarily mean that the atmosphere has the Earth-like content, but more terrestrial-like planets, also like Mars or Venus in our solar system. Now I will go through these types of processes shortly. And I start with the most classical form of the thermal escape, the Jeans escape. In this case, the atmospheric particles are assumed to follow the Maxwellian law. So the distribution of the particles can be written in the following way. Strongly depend on the thermal velocity of specific atmospheric species. With such prescription, the most energetic particles at the exobase, so at the level where the atmosphere becomes collisionless, and the collisions cannot prevent the escape anymore. The fastest particles can escape, and the criteria is that their velocity should exceed the gravitational velocity of the specific planet. In such an approach, the flux of escaping particles can be written in the following way, where it is pretty clear that the intensity of escape is strongly dependent on the relation between the escape velocity of the planet and the thermal velocity of the atmospheric particles, or in a more general sense, on the relation of the planetary gravitational potential and the thermal energy of its atmosphere. So, as evident, as this process considers mainly the collisional less atmosphere and the escape from the exobase, it's going to be most relevant for the compact secondary terrestrial-like atmospheres. And as it considers each specific atmosphere species separately, as the atmosphere is not collisional, it's going to be relevant for escape of the light hazes, for example, through the stable heavy element atmospheres, as it is the case for the present-day hydrogen escape at Earth. And also for the fractionation of isotopes and elements with different masses. Okay. This should be density of the specific species.
Density was maybe the total number of particles in that layer, like volume is units. I was thinking about units. Why is a flux?
Mm-hmm.
Is that a flux on the whole planet?
Mm-hmm. I think it is integrated, yeah. I think.
So then Ni must be some absolute number of particles.
Yeah, this number of particles is 1 per cubic centimeter.
Well, that's not absolute. That is density. That's just my point. I don't quite get it.
I think it is number density, yeah.
And then the place of flux thanks.
No problem. Speaking of the escape rates or the specific mass loss rates for this type of escape, they can be comparable to the hydrodynamic mass loss rates, which are the highest among all. Specifically for those planets which are close to hydrodynamic equilibrium. So it is the compact secondary atmospheres or some very massive and not too warm Jupiter-like planets. What should be taken with caution at this point is the real distribution of particles in the atmosphere is not quite Maxwellian. At least the fastest particles will be always removed from the atmosphere, and it's going to be a shifted Maxwellian distribution. But in general case, it can be more complicated, and one has to solve the Boltzmann equations. Next, the escape in reality does not occur also for such atmospheres only from exobase. It is some region nearby. And finally, and the most tricky one, the position of the exobase has to be known. And for exoplanets, for planets outside of our solar system, this is not necessarily the case. And for planets with hydrogen-dominated atmospheres, the position of exobase can move quite far from planet itself. Next, I will proceed with the kinetic escape processes, and most of the non-thermal escape processes consider the escape of the ions. And the atmospheric species can be ionized in through channels, of which the main process is the photoionization from stellar high energy radiation. But it also can happen through the interaction with the particles of the fully ionized stellar winds, or through the collisions with atmospheric electrons. In case of non-magnetized planets, these ions can be further removed from the uppermost layers of the atmosphere, for example, through the ion pick-up process, where the charged particle interacts with the electromagnetic field of the stellar wind and can be dragged away. But also, large fraction can be done by the photochemical reactions, such as photosynthesization in addition to ionization, and the collisions with solar wind particles, which can lead to additional heating, which intensifies any type of the thermal escape, or the production of the energetic neutral atoms, which have energies sufficient to escape jeans-like. Also, some atmospheric particles can be lost through sputtering. Such processes, together with such processes, are the dominant processes for the escape from terrestrial-like planets of the solar system. Specifically, they are relevant for the escape of more massive ions. And dominate, for example, the escape of oxygen, nitrogen, or the carbon species from present-day Earth and Venus. The escape rates for such type of the mass loss are significant for terrestrial-like planets. And for highly irradiated planets, they typically remain like an order of magnitude below the thermal escape, like a jeans-like or the hydrodynamic. For more quiet conditions, as for example at present-day solar system, they can even dominate the escape. But what should be taken with caution for exoplanets again, we do not really know in most of the cases the real contact of exoplanetary atmospheres, which is essential for any chemistry and essential for this type of escape processes. With inclusion of magnetic fields, the behavior of the neutral atmospheric material and the ionized one become pretty different. If the neutral particles can flow through the magnetic field of the planet without really noticing it, the ionized species wanna be trapped on the magnetic field lines. On one hand, it can decrease the escape because the particles which are caged cannot run away. On the other hand, in some cases can even intensify. Why? Because for more or less dipole-like magnetic fields, the particles going to be accelerated in the magnetic mirror until they reach the energy sufficient to escape either in space or to ionosphere. And the escape ionospheric plasma can occur through the open field lines. I think everyone knows that for the Earth, it is the polar cusp. Yeah. Well, well, not. Yeah, well, but they are not trapped quite forever. At some point. Yep. Yeah, this is also possible. So essentially, as I said, these particles can be removed to ionosphere, and then ionospheric plasma, which will also be affected by the X-ray, gamma ray heating, will go through the open field lights, or it can also be lost through the charge exchange process. So when the energetic ion hits the neutral atom of the atmosphere, and we get quite a regular ion, which remains, and the neutral atom, which has energy sufficient to leave the gravitational well of the planet. And additionally, as Rumi already told, in the presence of magnetic field, the numerous current system gonna appear at magnetopoles or across the ionosphere. But the general thing about them is they can provide additional heating, which in turn intensifies the thermal escape. So I will come back to it a little bit later. The inclusion of magnetic fields should be taken with caution, and the specific configuration has to be accounted for every planet. So again, the application here is quite clear. It is the magnetized planets with any type of atmosphere. And also such processes are relevant for the fractionation of ions. And the escape rates, for example, in case of the polar outflow, can be comparable to the escape rates in case of the hydrodynamic mass flows. So finally, I come to the hydrodynamic escape, which is my favorite one, because that's what I do. And as I mentioned, for the Jeans-like escape, the flux of escape in particles depends on the relation between the gravitational energy of the planet and the thermal energy of its atmosphere. When this thermal energy increases, at some point, the energy in the system becomes sufficient that the outflow can originate deep below the exobase. And the atmosphere escapes as some kind of the steady bulk flow instead of the escape of the separate particles. Hydrodynamical theory considers such outflow by solving the fluid dynamics equations, which consist of the essentially mass conservation, moment conservation, energy conservation equations, where the important parameters are, here's the source, which is typically taken to be 0, which assumes that there are no leaks or replenishment from the hydrodynamic atmospheres. Then it is the gravitational potential, which can be solely the gravitational potential of the planet, or can also account for the tidal forces of the host star. The thermal pressure and the energy of the particles, which is the sum of kinetic and thermal energies. And finally, parameter Q here is the sum of all heating and cooling processes. Typically, the main heating source is the photoionization of atmospheric material. So the process when the neutral atom absorbs the photon of high energy photon of incoming radiation, producing the ion, and the electron, which brings away the excess energy of this reaction, which can further be spent on heating. In this case, in simple way, the heating function can be written as following, where the integral essentially describes the spatial variations in the observed flux. And I is the number density of the specific species. Sigma is the absorption cross-section, which essentially defines at which depths the photons of the specific energy going to be absorbed. And parameter eta is a so-called heating efficiency parameter, which accounts for the fact that essentially not all excess energy produced in photoionization reactions are going to be spent on heating. Part of it will be also spent on the secondary ionization, for example. As a typical cooling process, we can consider here the Lyman alpha cooling, for example, which where the cooling rate is typically given by the specific reaction cross-section and the densities of the participating species. In reality, cooling processes and also the heating processes are much more. Essentially, it is any chemical reaction which goes with using or releasing some excess energy. And specific reactions depend on a specific model. So I will start discussing the hydrodynamic escape from the very classic case of the XUV-driven outflow. And here I show you the typical, very typical temperature profile for the moderate sub-Saturn-like planet, where we can see all the typical zones in the atmosphere of such planet. So the lowermost layer remains hydrostatic. The atmosphere is gravitationally well bound to the planet. But as we go upwards, the gravitational forces decrease and the atmosphere start to expand adiabatically and therefore to cool. Yeah, I did not say it is a one-dimensional model assuming pure hydrogen atmosphere. Yep, yeah, if we go to 3D, things get much more funny. But to describe the basic features, 1D models are the best. So the cooling proceeds until the point where the high energy radiation of the host star can penetrate and therefore being absorbed, where the heating starts until the point here, it is the sonic point up there, until the heating will be overtaken by the adiabatic expansion and cooling, which dominates the upper layer of atmosphere. So it is the classic scheme. And this type of escape can range in the escape rates can range in the wide interval between like 10 to 7 to 10 to 12 or even 14 grams per second. So a few orders of magnitude. And this type of escape is strongly dependent on the incoming X-ray radiation, and therefore it strongly depends on the type and evolution of the host star. However, even if however, besides the classic XUV heating, the planet can lose its atmosphere simply due to the combination of its low gravity and high thermal energy. As here I show as an example quite an extreme one with the atmospheric with the planetary mass twice that of Earth and the very puffy atmosphere, quite a lot absorbed. It's not very realistic, such planet not going to live. But the important point here, if the gravitational potential of the planet is small and the atmosphere is not very well bound, it's going to be expanded. And it can remain quite dense up to the Roche slope of the planet. So up to the position where the atmosphere does not gravitationally bond to the planet anymore, which is a typical, which is the upper boundary here. In this case, as the atmosphere is dense also up there, the stellar irradiation has problems to penetrate the atmosphere. So I show here the cases, the two cases with very different irradiation. Blue line is very, very high, red line is pretty low. But we can see that in both cases, I hope you can see at least something, the volume heating rate and the ion fraction remain pretty low. So the atmosphere is nearly neutral, and the heating, dependless on how much irradiation appears ineffective. In this case, if we look at the temperature profile, at the velocity profile, they look precisely similar in both cases. The atmosphere is simply expanding adiabatically, but the escape rates in this case can be even much higher than for the classic XUV irradiated way. So this one is a quite extreme example. Finally, what we have to account is the tidal effects in some global scale. Because if we consider planets that orbit heavy and low mass stars, the situation for planets with the same temperature going to look pretty different. As for low mass stars, the planetary system are much compact. At the specific equilibrium temperature going to be reached at much closer orbital distances. So I show here one specific planet. It is a typical sub-Neptune-like planet, quite hot one, 1500 Kelvin. But orbiting 0.8 solar mass star and 0.4 solar mass star, twice different, naturally at very different orbital separations. And I picked two models with pretty similar irradiation level. But as we come closer to the star, the position of the Roche slope also comes closer to the planet, which is exactly what we see here. The blue line is the planet around the massive star, and we have there the classic case of the XUV driven atmospheric mass loss. But for the low mass star, the Roche slope of the planet here comes very close to the surface. Here it is extremely close, 1.5 photospheric radii. And the atmosphere is very dense at the Roche slope, which results essentially in the Roche slope outflow. So simply the atmosphere is not gravitationally bound to the planet in the case. Again, the case I show here is very extreme. But also for more moderate planets, tidal effects can have significant effect, specifically for low mass close-in planets. So now I come shortly back to the magnetic fields. Now, as we pass through all escape processes, there exists a paradigm that the presence of magnetic field is necessary to protect the atmospheric the atmosphere from escaping. And indeed, if the atmosphere of planet is compact enough, the presence of magnetic fields at least means that it does not interact with the stellar wind directly anymore. However, everything depends on configuration. And this was, for example, shown for terrestrial planets in solar system, specifically for Mars. It was studied a lot, that the weak magnetic field can intensify the escape. In case of Mars, the magnetic field is the crustal magnetic field, so not the global dipole, but it demonstrates that essentially the configuration of the field can matter. For cold Jupiters, different models predict indeed the reduction of the escape if the magnetic field is strong enough, where the border values are different for different models. But for more moderate planets, specifically, I show here the figure from Carolina 2021. It was shown that the reduction of the escape by catching the ion closed lines can be overdriven by the polar outflow. Here's the simulation for sub-Jupiter planet, where the green and yellow lines show the escape through the poles, and the blue line shows the escape from the night side, so the tail. And one can see that with the increasing dipole strength, the escape through the poles intensifies, while the escape through the night side decreases. But in sum, it can even lead to the increase of the atmospheric mass loss rate. So again, it looks like the specific effect of the magnetic fields is not yet quite clear, and it might depend on the type of the atmosphere. It might depend on the specific configuration of the field, and naturally on the stellar environment. Now, finally, I come to some simulations, and
do not take into account the relative motion of species, and then they get completely different results because the pole is usually not the case. So it's model dependent.
Yeah, it is model dependent, which is
far away.
Mm-hmm. Well, it is far away from any conclusions at this point. So
I would say science. Right. Yes, we are getting confused, and even we're seeing Saturn, and then something happens.
okay. I hope something not going to happen right now. It's just a nice overview talk. So now coming a little bit closer to our work and the atmospheric mass loss rates. Here I consider the atmospheric mass loss rates across the very different planets. Specifically, I show in the top panel the atmospheric mass loss rate against the gravitational parameter, the Jeans parameter lambda, which is essentially the relation of gravitational potential of the planet to the thermal energy of its atmosphere, taken at photosphere. And each dot corresponds to one model planet, where the parameters range between 1 and 100 Earth masses, 1 and 10 Earth radii, and these planets also orbit at very different orbital separations around stars with different masses. Yep. This parameter can be calculated at different distances. So typically for the Jeans-like escape, they use the similar parameter lambda, typically written as small one, and they calculate it at exobase. So instead of the equilibrium temperature here, it's going to be the exobase temperature, and instead of planetary radii, which is the photospheric radii for the observed planets, going to be the exobase position. Nope. It's very solid. It's simply the gravitational potential of the planet to the thermal energy of the atmosphere. Nothing else. So, and we can see that it has two distinct regimes. On the left, which is dominated by low mass, it's clear from the parameter by low mass planets, the hot ones and the very inflated ones, so massive atmospheres on relatively small cores. The atmospheric mass rates decline quite steeply with increasing gravitational potential and with decreasing thermal energy. While for planets on the right, which are mainly the more massive, more compact and cooler planets, the dependence is quite much more moderate. If we look at these two specific groups, at the atmospheric mass loss rates for these specific groups, and compare them to the stellar XUV flux, which the planet gets, we see that the group on the right depends strongly on the XUV heating. So the dependence on XUV flux is nearly linear. While the group on the left, the crazy guys, they depend on very weakly on the insolation, if they do at all. So what does it mean? Essentially, this group is clearly dominated by the XUV-driven atmospheric mass loss, while the guys on the left are mainly losing the atmosphere due to the own thermal energy and the low gravity. So to put it in the context of planetary evolution, I consider here a few evolutionary tracks from our paper from 2021, or one planet, Kepler 411d, which is a relatively cool planet at, I think, 0.2 AU from its host star. And a few models for K233b, which is the planet around, for Kepler 411 is very much evolved star. And K233b is at very close orbit around the young star. But it has no mass constraint. That's why we consider a few models between 7 Earth masses, the red line, which loses its atmosphere within 100 million years, up to 30 Earth masses, the magenta line here, which keeps most of the atmosphere until the end. It doesn't lose even 1% of it, I think. And the changes in radii, in this case, are purely driven by the thermal evolution of the planet. So the core of the planet cools and the planetary atmosphere contracts. The different circles mark the specific times. So it is 10 million years, 100 million years, 1 and 5 gigayears. And if we consider this, if we overplot these tracks over our mass loss diagram, we can see that for low mass planets, the red and the yellow, 7 and 10 Earth masses, they start their evolution, all move from left to the right. They start their evolution on the left-hand side. So they are just so much inflated that the atmosphere is essentially not stable, but they do not remain there for long because the atmospheric mass loss rate is pretty high. The atmosphere will be lost quite fast, and also the cooling speeds up. So already at 10 million years, they come into the transition region, and at 1 gigayear, they land up in the XUV-driven escape-dominated region. The more massive planets, also those which orbit an active star and those closely to active star and those orbiting relatively far away. So the green line is nearly not affected by the mass loss. It does not lose any of its atmosphere. Well, a little bit. They spend like most of their life in the region with the XUV-driven atmospheric mass loss, which means essentially that the XUV-driven escape will be important, and specifically on long scale evolution of planetary atmosphere. And as XUV-driven escape is important, the evolution of the host star becomes important as well. Here I show the plot from 2015. And what it shows is essentially the XUV luminosity of the star is closely bound to its rotational rate. All stars begin in the so-called saturation regime, where the XUV luminosity only weakly depend on the rotation, but leave it at some point as the star slow down, the spinning of the star slow down. As the stars are not born with different, with the same initial rotational rates, but very different, they leave the saturation regime at different times, which leads to the widespread in possible stellar XUV luminosity at the ages between like the protoplanetary disk dispersal, where the atmospheric escape begins, and about 1 gigayear. And as most of the planets are strongly affected by the XUV-driven escape through their lifetime, this difference might be important. But also, these tracks do not look the same for stars of different masses. This spread in XUV luminosities at young age is much more pronounced for the heavy stars. To see how much the effect can be, we have applied it to the population of low mass planets between 5 on the top and 20 Earth masses, orbiting at different distances around half solar mass star, 2 left columns, and the solar mass star, 2 right columns, and starting their evolution with very different initial atmospheric mass fractions. So the first attempt to account for the different formation scenarios between fractions of percent and 30%. And for each 2 panels, the left column corresponds to the planets, the evolved planets around fast rotator, and the right one around the slow rotator. And what we can see, the first which jumps at the eye, is the differences in the possible differences in the stellar rotational histories are much more relevant for the heavier stars. So here we see clear difference between the two. Here, much less. And another thing, funny thing here, there is some kind of the sweet spot in the initial atmospheric mass fractions, which is pretty well seen here. I did not say the color shows the final atmospheric mass fraction, how much atmosphere the planet preserves. And one can see that if the planet starts with relatively compact atmosphere, it can keep it, while with very inflated ones or pretty tiny, it is not the case. Yep.
That's the rotation. Is that a proxy for the actual effects?
Yep.
Or is it actually the rotation in some sense?
Well, we do not include the rotation at the hydro models. Our hydro models are for planetary atmospheres, but we account for different rotational evolution. So here we employ the Morse models from Johnston 2021. We set different initial rotational rates and use the evolutionary tracks for these stars. So for fast rotator and slow rotator, we simply take the data for stellar clusters at 150 million years and the distribution of the rotational rates as it is, and take one value at the upper part and one value at the lower part. We do it for stars of different masses, but actually the initial rotational rates in both cases are quite similar for fast rotators and for... Yep, at the young ages. Yep. So we take, the extreme cases for each star and how much difference they can make. It is essentially the blue line and the red line here. So we take this one and this one. So you can see that the reason partly is simply that the evolution of low mass stars, M stars, is not so different. The spread is not so large in terms of XUV. By the way, another thing which we notice in this study is that for the similar planetary temperatures, the escape is much intenser for low mass stars. So, finally, I will show you some results from our last paper, which is dedicated to mass radius distribution, where we consider the observed mass radius distribution here on the right for planets between 1 and 100 Earth masses. And with temperatures between 500 K and roughly 2000 K, which is dictated by our hydrodynamic models. And the observational bias, we have to have sufficient amount of planets. Here, each point corresponds to one observed planet, and to plot the lines, we have considered the model planets in the similar mass range. And with the similar temperature range, specifically we considered 5 orbits around the solar mass host star. And we also considered 2 different stellar rotation scenarios, again, the slow rotator and the fast rotator, which are shown for each color of the solid line. It is the fast rotator case. And here the short dashed line is the slow rotator case. For the initial atmospheric mass fractions that are predicted by the formation model of Martassini 2020. Additionally, we consider the planets starting with much more massive initial envelopes. This is the very upper line. And for this, we only consider the slow rotating star because we want to set up the upper limit. And for these planets, we assume that they have formed somewhere beyond the ice line and then migrated inwards through the disk phase. So what we wanted to understand here is how much will be an input from the stellar rotation history and from the initial parameters of the planet for the specific case. And do we need to focus on one or another when we analyze the present day populations as we see it? And here are the red lines for hot planets, for the hottest planets in our sample, the blue lines for the nearly the coolest ones. And you can see that our model predictions on the radius spread outline the observed population quite well, except of these hot Saturn planets, which are expected to be affected by the inflation. I will not stop on it today, but you can always come to me and ask. And another thing which we see here is that for the cooler planets, here are 2 cases with different initial envelopes, very different. But we see that 2 lines are merged at around 7 Earth masses, which essentially means that initial parameters do not matter here, because for low mass planets, if you put on just more atmosphere, it will just escape faster. So they converge, while for the stellar rotation, we see quite a wide spread. When we go for these planets towards the more massive ones, we see that the input from the initial parameters is quite substantial and actually overcomes the effect of the stellar rotation, which is just that, which makes not more than a quarter of the whole spread. When we go to the hot planets, the orange lines, we see that these 2 lines do actually never converge until the atmospheres are fully evaporated. So these are naked cores or the secondary atmospheres, which do not add much to the linear. And here the input from the initial parameters, so from essentially the specific formation mechanisms of the planet, is dominating for massive planets clearly, and at least comparable for the low mass ones. In the plot on the left, we see it a little bit in a more simpler way. Here, the shaded areas show the radius spread predicted for different specific masses by our models, while the dots, the green one accounting only for the stellar variability, the yellow one adding up the various initial parameters. And we can see that for low mass planets below, let's say, 10 Earth masses, we can describe the whole spread essentially not accounting for the specifics on the formation so much, simply from the variability in different stellar evolutions. But for more massive planets, the two, we do need to account for both to explain the whole spread. And finally, there's one more odd thing which I want to show. If we look closer at the planets with in different temperature ranges, so hotter or cooler, we can see that, okay, for hot planets, our models reproduce the spread quite well. But if we go to cooler planets, we find the whole population of outliers here and here, which is represented by relatively massive planets, like between 10 and 40 Earth masses, which are much denser than is predicted by our models, which assume the rocky core and the hydrogen-dominated atmosphere in the beginning. The possible solution can be either much stronger escape, so some escape process which we do not account for, either some major differences in the formation processes and so in the composition of planets. For example, the radii of such planets are comparable to those of the icy cores or the water-like planets. And what should be also pointed out, there is some observational bias. Due to observations we detect on the close-in planets. So the hot mass planets is dominated by solar-like stars. But as we go to the lower temperatures, the fraction of the low mass stars increases. Here it is yet K stars. And for the very cold ones, these distributions are dominated by planets orbiting low mass stars. So the last thing which I say here is that there is something we do not pretty well understand about the planetary population, about M stars, and that might be lying somewhere in the formation of these planets, in their compositions. With these open questions, I leave you. And I'm happy to take any questions.
So thank you very much, Daria. So I guess there are a couple of questions or plenty of questions. Okay.
I have plenty of questions. Can I just start with two very simple ones? On page 13, you said hazes. And of course, this makes me jump because now I want to figure out what kind of haze is. I really mean hazes?
Did I really say hazes?
Yes, you did. And I thought, okay, 13.
At the moment, that's quite a way to go.
Yeah, that gives people time to think about their question.
They have already asked.
Look, escape of light hazes from stable heavy element atmospheres.
No, well, by light hazes, I meant simply the light elements here.
Oh,
not really hazes in
no hazes.
The sense of the...
Good, right. And then on page 18, can you just move forward? You said energy plus pressure, and I'm confused here by units, but I didn't want to put in another unit question. You see in your energy conservation, the advective term says VR squared E plus P. And then you say it's the thermal pressure, but it's yeah. Maybe it's just a typo. It's an energy density, right? And the other one needs. But then, okay, then the other one is also an energy density. We can talk about this offline or think about this offline.
So maybe I have a question. So you did this 1D hydrodynamic model at the equator of the planet, or
at the substellar point.
Okay, yeah. So you did it maybe at higher latitudes as well?
Well, we did also 3D modeling, and well, the escape rates are not exactly the same, but it is comparable.
Okay. Yeah, Peter?
I have a very basic question to the definition of the exobase. I think when we are considering only, say, neutral particles, then you can do collisional cross sections with a fixed cross section. But often at these distances, you have ionization. So you rather have free electrons, ions swirling around. And then it might be more appropriate to actually use some kind of Coulomb cross sections. And this is, which are much, much larger. So where is then this atmosphere becoming collisionless? I mean, I know this is sometimes used, this argument that you can do hydro whatever. So beyond the exobase, because...
No, that's not a very good idea. Okay, no, it is the case that for ionized particles, the position of exobase will change. So typically, when people considering the Jeans-like escape, they consider it for the neutral particles. But in case if the atmosphere is fully ionized at the higher levels, as it is typically the case for hydro models, the cross sections which you use, I think, should be different.
Is this somehow going into your hydro models, these kind of considerations? Do you need that at any point in your models?
No, well, for hydro models, I don't need it, except of the moment I have to make sure that the exobase is not where I calculate my escape rates. So typically, we simply make sure that the exobase is not below the Roche slope or is not in subsonic region somewhere, because then all our calculations become senseless.
Essentially kinetic, so hydrodynamics is inapplicable.
Yep.
As far as you use hydrodynamics, then you automatically assume you are still in the collisional region. So that you describe your media as a continuous media, not ensemble of particles.
No, we simply calculate the Knudsen number just to make sure that we don't make some stupid thing.
Are there more questions? So online, I don't see any questions. So maybe one more from me. Okay.
So how much would your work profit from a better understanding of the host stars? So I'm now diverting you to Plato, etc., and staring at the host stars until you know everything of it. Is there any benefit from this for your research?
Well, naturally, because as I have shown, the evolution of the star is pretty much important, and observing many young stars in particular would be pretty useful, because the models which we use is some kind of a combination of the theory on the rotation and the empirical laws which are fitted on the observations. So the observation in young clusters of different ages and what is predicted by these models is essentially some kind of the average for the mass of the specific, for the star of the specific mass and specific type. But the real numbers can actually spread around this value quite a lot. So any improvement here would be of great use.
Did you actually apply this model to our solar system? So for example, Mars?
Well, if I apply hydrodynamic model to Mars, it's over very fast.
I mean, now it's done, yeah, but just in the past, for example, how it lost its atmosphere?
Myself, I did not do it, but you can ask, I think the group of Helmut knows more. But whatever hydrogen atmosphere at Mars does not survive longer than a few million years, I believe.
Connecting to this question, did you also look into, when you assume, for instance, you had the Earth mass planet, so if a planet accreted an Earth mass in the primordial and in the planetary disk, are there cases where it will not lose this hydrogen, which may be captured or accumulated over time? I mean, what I mean is it possible to have an Earth mass planet with a hydrogen envelope, which never was lost
Well, the
in a
Earth's
habitable
mass
zone
probably
if it's
not, but
close, of
actually,
course.
if you increase the mass and in the position of the Earth, it could keep the hydrogen-dominated atmosphere if it is like 1.5 Earth mass, I guess.
Depending on
Already,
the
so
stars.
we are like pretty much on the border a little bit more, and we have a hydrogen-dominated atmosphere, not so much. It would be tiny, but it would be enough to prevent the creation of the atmosphere as we know it today.
Okay, thanks.
Okay, two last questions, okay?
Atmospheric electrons. There was some slide that says atmospheric electrons. Of course, electrons also plays a role in a sense. If you have magnetized, you might have precipitating electrons, or they can also modify your ionization, or even if you have ionized, you might come back again. That this is something, but at Earth, it's still not so clear, you know, how this polar wind or I mean, this business is partly also not really solved yet in the Earth. So
well, that's the case.
Yeah,
we understand everything on a global scale.
Right. So maybe it's also good to
the devil in details.
Yeah, and maybe there will be more data coming up because you have more GDC and low Earth satellites coming more, and people are more interested in the low energy ions in the magnetosphere. So maybe there might be also commonality that we can compare more based on your model, or it's this input output from the Earth-based mass loss might help you, or people are talking also how the solar activity or the host star activity changes more based on other product like this tree how to say this carbon 14 so that you have much more information on the solar cycle than what we used to know. So maybe you have more information eventually which you can combine with your kind of model about the mass growth. I don't know, but yeah, I mean you can easily go to other planet, of course, but also Earth, it's still not clear. So
well, that's the case. Yeah. I mean, when it comes to the process like ion escape, it is already quite far from the hydrodynamic stuff that I do. And using these models, well, we can constrain to some extent the activity level of the host star in the past, also through the fractionation of elements which are more abundant, or in a more general case, as we do for exoplanets, we just consider the present-day parameters and see with which combination of initial parameters and the stellar activity we could reproduce them. But in lots of cases, it's quite a poor constraint. So in the lucky cases, we can do like constrain plus minus 20% for the rotation rate for the activity level, essentially. But for better accuracy, we don't only need the better observations. We also, well.
Can I? So my question is also somehow about Earth's atmosphere and evaporation, thermal and non-thermal processes. And I can imagine that in the near Earth space or in the terrestrial atmosphere, we have much more measurements. And therefore, we can think about one-dimensional, two-dimensional, three-dimensional fluid scale kinetic models, right? But I can imagine that in those models, there are plenty of input parameters which can be somehow measured, or we have to wait for further missions, okay? However, you are showing statistics of many planets parameterized by few parameters. And I understand that we cannot use those complicated models which are available for the terrestrial atmosphere because simply we do not have so many parameters under control. Is it so, or you see some simple ways how to make these models more complicated? Do you understand my comment or question? I am not sure if it is a comment or question.
I hope so. Yeah, it is exactly the case. We do not really know so much about the atmospheres of extrasolar planets. So whenever we want to make some kind of the model accounting for the ion escape or for whatever kinetic stuff, we need to know quite a lot of things. So there are attempts, but it might be quite a lot of manipulation because people simply assume the specific atmospheric content and the specific atmospheric content alone is enough to make things wrong. Because even in solar system, we have like 3 terrestrial-like planets. The atmospheric content is pretty different for all 3. And naturally, the modeling should be different. For exoplanets, we do not know a lot. That's why we resource ourselves to the hydrodynamic models. We look at much more basic things like the hydrodynamic atmospheres, if they are removed or not, if they are yet there. So we can look in this sense at some kind of the population of observed planets, but like on the basic scale, I would say.
Maybe a comment to this. So, Zoltan, you're right, this quite complicated stuff, and you need a lot of data for getting really these detailed escape rates, which we do not even know at present in Earth exactly. But these are different. So all this here, like on Earth or Mars, Venus, these are secondary atmospheres. And the escape rates, I mean, if you add 3 satellites more or 10 satellites, what we know is that we know more or less in an order of magnitude. It will not change anymore. So, for instance, on Mars, you can fly 10 satellites in the future. You measure then some details, but it is all within a order of magnitude. This may be relevant for, and you go really in, depending on the scientific issues you are in. But in this case, we're speaking about primordial hydrogen type atmospheres, and these escape rates, what Daria, all the escape rates she showed here, there is this hydrodynamic escape or thermal escape in the case if it's a small body, very hot, close to a planet. These are the main drivers. So I think that these results are very, I would say, quite valued, even if these are planets so far away in that sense. The main unknowns are the evolution of the host star's radiation, or some, of course, you need some as good as possible planetary parameters, radius, mass, in that case, if it's such a hydrogen type atmosphere. And most of these planets, what you had shown, even if you do not have the data that's an hydrogen atmosphere, but from these transit observations, you know, I mean, you cannot have a CO2 atmosphere which extends up to these distances. There are a lot of logical scientific indications that these are hydrogen, helium, primordial type atmospheres. And getting back to your question, it's true, for instance, we do not really know exactly, also connected with the magnetic field, from data we have from Venus Express, Mars Express. These are 2, and from Mars we have a few more spacecraft, and we have a lot of some other spacecraft on Earth. The escape rates are quite similar. So Earth has a magnetosphere, Venus has no magnetosphere, it's closer to the planet. But you should not forget, and I think Daria mentioned it, that the planets have different atmospheres. And people focusing only on the magnetospheres and plasma physics mainly ignore then the atmospheric structure. So if Venus would have a nitrogen atmosphere like Earth, the escape rate would be different. Because also the atmosphere structure will be different, and then you have a larger cross-section for the solar wind interaction that you have not on the CO2. So, but these are crucial and interesting things which should be studied in more detail in the future, and with when we get some data, of course, from future satellites. Also for the Earth, it's not clear. I think maybe Rumi mentioned it or addressed this. When we speak about polar outflow, it's not so clear that all ions will really escape. And so there's a lot of things which should be investigated in this type of planets, but they are different, of course.
Okay.
Okay. The very last word. I think we have a very beautiful example for this problem here. This is the weather forecast on Earth. When we applied the same codes to an exoplanet, it was a disaster. And we realized eventually, step by step, why? Because so many knowledge about the Earth was hard coded in that in this hydrodynamic simulations, and it started with the temperature pressure profile, which of course is a nightmare for every astrophysicist, because this of course evolves. Then I guess if you want to reach a comparison, we have first to agree on a level of approximation, and then we can do a comparison. But requiring the same level of depth for the Earth and for an exoplanets like we have on Earth, we are getting stuck in our knowledge on Earth. So sorry.
No, these were very nice final words here. Daria, you want to say anything else? Otherwise, I would say let's thank the speaker again. And thanks for joining also out there in the ether. And we will meet next Thursday for the colloquium. Thank you very much.